Good morning, students. This is topic 7, video E, electron affinity. We have one more trend to consider, electron affinity. In the chemical literature, electron affinity has been defined a couple of different ways. We will choose to define electron affinity as the heat released when a gaseous atom gains an electron to create a negative ion. This is the definition Linus Pauling used in his famous book, The Nature of the Chemical Bond. Linus Pauling is perhaps the most famous chemist of the 20th century. He won not one, but 2 Nobel Prizes in chemistry and in peace. So let's use his definition. The chemical equation corresponding to this definition of the electron affinity is shown symbolically here. For chlorine and oxygen, the delta H of the reaction is negative, telling us that energy is given off. We define the electron affinity as minus the delta H. This means that the more negative the delta H value, the more heat is released, and the larger the electron affinity. This means the ion is more stable than the atom. Electron affinity values are tabulated. Let's look at chlorine to be sure we can interpret electron affinities. When an electron binds to a chlorine atom, energy is released and the electron affinity is positive. We see that chlorine has the largest number on the table, so we say that chlorine has the greatest electron affinity. The electron affinity is a measure of the energy released. When the chlorine ion is formed, 349 kilojoules per mole of energy are released. This is a favorable process, and the chloride ion is stable compared to the isolated chlorine atom. In fact, all of the group 17 atoms exhibit favorable electron affinities. These are called halogens. In general, electron affinity decreases as you go down a group, and is consistent with the trends observed in ionization energy and atomic size. We can explain the trend by looking at electron configurations. For each of the halogens, the electron configuration shows a p5 valence shell. They all readily accept one more electron. As you go down group 17, the elements get bigger. The electron added is further from the nucleus, and so the attraction to the nucleus is weaker. We could also say that the binding energy of the electron is lower. Let's return to the electron affinity table. While in general, the electron affinities get smaller as you go down a group, there are some clear exceptions. The atoms in the p block of period 2 have electron affinities that are somewhat lower than the atoms in period 3. This is probably because the period 2 atoms are extremely small, and the electron-electron repulsions are greater than in period 3. Notice that the metals have significantly lower electron affinities than the halogens. Also notice that the noble gases and a few other elements have no electron affinities listed. The formation of an anion from these elements is not favorable. You don't need to memorize the numbers in the electron affinity table. You should, however, recognize that atoms with positive electron affinities form stable anions, and you should be able to use an electron affinity table that is given to you. Now let's practice a multiple choice question. Pause the video here and take this opportunity to synthesize your knowledge on periodic trends. Write the answer in your notebook. The answer is A. Try writing a couple of other questions that vary these relationships. Writing things down is an important part of the learning process. Hopefully your notebook is your own, is creative, and could even be a work of art.